session will focus on the future of space exploration appropriately. Our moderator for this session is Professor Edward Crawley. Ed's the director of the Bernie Gordon MIT Engineering Leadership Program. He's also a Ford Professor of Engineering, and he has appointments in both the Department of Aeronautics and Astronautics and Engineering Systems. Ed's research focuses on the domain of architecting and designing complex technical systems, and he's spent a great deal of time looking at architecting complex technical space systems in particular. He's a former department head in AeroAstro, and I had the pleasure of serving as his deputy during part of that time. He is also on the Augustine Commission, which has recently been named, so he has a very unique role in looking at the future vision for space exploration. Ed?
Thank you, Ian. Space has become a ubiquitous capability in our lifetime. We drive around with GPSs in our cars, watch television shows that were beamed down from satellite transceivers. We get scientific results back from space. We monitor the condition of the climate of the Earth from space. All of these things are accomplishments of the past, and hopefully will carry on into the future. What we are going to be discussing in this panel session is the future of space and of space exploration. But before we go to that, I want to point out just how ubiquitous the success of space has become in popular American culture. Since the advent of satellite radio, I've become a country music fan. Not something that a boy who grew up in New England would likely to have happen if you just had to listen to regular AM and FM radio. So I was bebopping down the road one day, listening to this Rodney Atkins song, and here's the refrain. The song is called "It's America." These are all the iconographic images of America. A high school prom, a Springsteen song, a ride in a Chevrolet, a man on the moon, fireflies in June, and kids selling lemonade. Cities and farms, open arms, one nation under God. It's America. We're going to hear it now.
My glass, smiling, thinking to myself, man, what a picture perfect postcard this would make of America. It's a high school prom, it's a Springsteen song, it's a ride in a Chevrolet. It's a man on the moon and fireflies in June and kids selling lemonade. It's cities and farms, it's open arms, one nation under God.
It's America. Now, the interesting thing is that I listened to that song tens of times, and I could have sworn that that line said, "It's a man on the moon in 5 flights." And I said, 7, 8, 9, 10, 11. Boy, this Rodney Atkins guy, he really knows his space history. But of course, it actually, when I was preparing the script, sounds to read, "A man on the moon and fireflies in June." I have 3 laws on spaceflight. Kepler and I have 3. Mine might be more useful. The first one, I'll reveal the 3 of them to you over the course of this session. The first one is there are many uncertainties in the future of spaceflight, but the one thing I can say with confidence is that every 2 years there will be a congressional election and every 4 years a presidential election. So space missions and space programs must be designed to continuously demonstrate value to the American people in a demonstrable way and in a cadence that's associated with this pattern. One of the unquestionable sources of the delivery of value to the American people is in the scientific space program. And our first speaker today, who will address that in her keynote, is Maria Zuber, the professor and head of the MIT Department of Earth, Atmospheric and Planetary Sciences, a member of the Aldrich Commission in 2004, which chartered the initial direction of the vision for space exploration, sort of the bookend, the one that I'm now going to spend my summer vacation working on. She's also the principal investigator of the GRAIL mission. This is MIT's mission, which will send 2 scientific spacecraft to do gravity mapping of the moon in the year 2011. Maria?
Great, thank you very much. You have no idea how excited I am to be here today. Last fall, Ian and I got together. He said he wanted to talk to me, and his opening comment was, "Run and hide, I need your help." And then he told me about this event and what he wanted to do, and we came up with the ideas for the Women in Aerospace event and the Sally Ride Science event. And how could you stay away from these things? What an honor it is. My parents let me stay up late to watch the Apollo 11 astronauts walk on the moon. I wrote long letters to every Apollo astronaut telling them my impressions of the missions and asking them about theirs. And none of you guys ever answered me. But every time I sent a letter, NASA sent me an autographed picture of the astronauts from the mission. And I took that as great encouragement, and I'm still around, so it doesn't take much to encourage and inspire. Okay. Today, in the short time I have available, I want to just offer some thoughts about how to move ahead. Okay. And I thought I would start here with a recipe of what I consider to be success. My experience has been in robotic spacecraft. I've flown over 6 experiments, and I have several experiments in space right now. So, but I wanted to give this talk, I think, to do honor and justice to the magnitude of this event. To think more broadly about than just my own field, but to think about the full suite of science that might be possible, and also to bring into that human spaceflight. So what's the recipe for success in future space exploration? Well, I think certainly there needs to be exploration and discovery. Every time we've ever been somewhere that we haven't been, or we've ever looked at something with a different set of eyes or a different wavelength or a different spectral resolution, we've discovered something. So discovery is assured when we go out and look. I also think, very practically speaking, that it's very important that we contribute to human well-being, and certainly the capabilities that we have in space contribute to that. And just to give you an example from what we saw this morning, the image of Earthrise taken by Apollo 8 as it came from behind the moon, and the image of the Earth that Jack Schmitt took looking back at the Earth as Apollo 17 went to the moon, I think profoundly changed the way about people think about the Earth, and certainly contributed in a very positive way to our humanity. And so those are just 2 examples, but there are many practical examples as well. Any program that we have for space exploration really needs to be reality-based. It's great to be a dreamer, but the only good space mission is one that's in space, really working. So the greatest ideas that one can come up with for all the wonderful things that one can do, if they're not practical and they're not implementable, then their time has not yet come. And I'm very much a person who likes to think about the future but live for the present. We need a mixed portfolio. NASA has gotten into trouble in the past by going to all big missions and then going to all small missions, and I will describe a number of examples of a mixture of small, focused objectives and large, grandiose things that can only be done with major, major technology investment. The combination of those two, I think, will lead to a healthy program. And so in keeping with that, I think balancing spaceflight heritage and technology development, in order to get the best people excited about being a part of the space program, you can't just simply take off-the-shelf hardware and refly it every single time, okay? Although for some applications, spaceflight heritage is, of course, very useful, but if you only fly what you've flown before, you'll never fly anything, actually, because nothing will have ever flown. The human presence in space, I'm a huge fan of the human space program, but I think the human presence in space should be for objectives which are worth risk. And so in this way, I echo some of the comments that we've heard earlier today. I believe that humans and robots should work in space together to their optimal advantage. I believe that things that could be done by robots should be done by robots, but there are plenty of things that humans can bring to spaceflight exploration the robot can't bring, and I'll give you an example of just one of those things. And I think it's also crucial that we inspire and train the next generation. When I was on the Aldridge Commission, we traveled around the country, we held town meetings, and we held hearings, and I was absolutely astonished at the hundreds and hundreds of people who came up to me and told me how they became interested in being a scientist or an engineer because of getting to watch the Apollo missions. And it's a non-quantifiable arrangement. By and large, I can't remember any of these people that actually worked for the space program. They were telecom engineers, they were biologists, they were electrical engineers. But they realized that the math and science that they took in school could just have really a magnificent application of doing things that they were good at. And what you don't see in here in the Aldrich Commission, one of the things that we found is that certainly national prestige, international cooperation, all of these things, if you do all these things, the rest will follow, okay? And all of these will contribute. Okay, so in the 20 minutes that I've been allotted, we can't possibly cover all of what could be done in space exploration. So I'm just going to choose a number of examples and talk about them at a very high level. In some cases, they deal with particular missions or programs that have been suggested in decadal studies or in commissions. In other cases, I think that they would just be interesting questions to study. It's not at all clear that all of these could be done, certainly in any particular sequence. And I do believe very, very strongly in presidential vision and in community input and bringing all of that together to bring together a great program. So, so this is not going to be comprehensive by any stretch of the imagination, but illustrative of some of the points that I listed in the last slide. So, a bold, diverse agenda in space could study human physiology, measure the variability of the sun, determine the extent and composition of the universe, discover other Earths in other solar systems, sustain our planet, and seek extraterrestrial life. And I will give you an example or two of each of these examples. Okay, Human physiology and behavior. Okay, this is basically this is just an example. I mean two things by what I'd like to talk about here. The first is that if humans are going to have a long-term presence in space, and I believe that they should, then we're going to have to monitor physiological and behavioral effects over the long term. This is taking place now. It needs to continue to take place. I think putting in people into space just to do this is probably not justification of itself in the risk, but doing other interesting things, certainly this kind of information should be collected. The second point that I mean by this slide is to say that, to follow on John Holdren's comments from the last session, and to say that we really need to think about a plan for the International Space Station. A great deal of effort has been and is being invested in assembling it in space. It is an absolutely magnificent facility. I believe there are one or more Nobel Prizes to be won with science that could be done on the space station for the reasons that I talked to before about being in an environment that you're not in and studying something that you haven't studied before. I'm not sure if that Nobel Prize is in the physical sciences, the biological sciences, or someplace else. But I think thinking about how to make use of this facility that we have invested so much and in good cooperation with international partners, I think is an extremely worthy goal. The variability of the sun, okay? The sun, the behavior of the sun is important for so many reasons, okay? And we have only been able to measure solar irradiance from a spacecraft since the late 1970s with the Nimbus 7 spacecraft, and it looks like there are decadal variations in solar variability, and certainly this comes into questions about what is the role of the sun in climate in terms of what the flux of the sun is, and also what is the effect of the sun on the upper atmosphere, on convective patterns, clouds, et cetera. And solar predictability. Another reason that we need to understand the sun is that successful robotic and human exploration will require the prediction of space weather in the heliosphere. And this is a beautiful picture of the solar photosphere by the TRACE mission. But the interesting thing about this, so this is a very practical application about a measurement that is going to be very important if we're going to send humans into space for extended period, if we want to think about an outpost on the moon. But it's a very interesting scientific question as well, because the sun, the heliosphere, the Earth, and the planets form a coupled system through a whole variety of space physics processes, and trying to understand the interaction between those processes and how they all fit together is just a fascinating systems problem. With the recent flyby data that we've collected from the Messenger spacecraft at Mercury, the coupling that we're seeing between the heliosphere and the surface and Mercury's magnetosheath, it's just fascinating how dynamic, what people thought this was a dead planet, but there's actually a great amount of dynamicism that is taking place. And understanding this, I think, is just a fascinating scientific problem. Okay, we're now going to move on to astrophysics, and in fact, we're going to move on to the edge of the universe. So the universe is somewhere between 13.5 and 14 billion years old, and we have a mission that will be launching hopefully on about the 2014 timeframe. The James Webb Space Telescope. This will be at the L2 point, 1.5 million kilometers from the sun, away from the distraction of the Earth. And this mission will actually be able to measure or detect and image the first galaxies that formed after the Big Bang. What a fascinating thing to do, to go back and see the universe in its formative stages. Okay, that doesn't appear to be working. Okay, what I was going to show on that slide, and I'll just talk about it if I can remember what I was going to say, was the constitution of the universe. And one of the fascinating observations that we have made in about the last decade or so, actually it's been a variety of independent observations, has been the suggestion of a force called dark energy, which would make up about 3/4 of the mass of the universe. So it turns out that there's a disconnect between the geometry of the universe and the amount of matter that we know about. And this has been determined from Hubble Space Telescope observations of type 1a supernova stars, as well as measurements of anisotropy in the universe. This is a map of the cosmic microwave background by the WMAP spacecraft, and it shows that the universe is basically flat, which is basically calling for something with negative pressure to be filling the abyss, or else something quite unusual happening, like a breakdown of the inverse square law of gravity at large distances. And this gets down to the basic question of exactly what is the universe made of, and it is a very worthy goal for future exploration. Okay, next, I don't think I have to tell anybody about the excitement of directly detecting and characterizing terrestrial planets beyond the Earth. There are suggestions of a mission called the Terrestrial Planet Finder, which think about 2 ways of detecting planets, terrestrial-type planets around other stars. So if you have a terrestrial planet around a star in another system, there's a variation in brightness of about 10 to the 10th over a distance of a fraction of an arcsecond. And so it turns out to be incredibly challenging to separate the two. And there's 2 ideas for doing this. One is to put an internal coronagraph in a spacecraft to block out the central star. The other calls for a nulling interferometer, where we put spacecraft flying in formation, in very tight formation, in which we have the light coming in about a half wavelength apart, so we can have destructive interference and cancel out light that way. And Terrestrial Planet Finder, these 2 aspects of it have been in planning some time, but there is not really sufficient funding in the budget to move ahead with it. We want to do more than simply detect planets around other stars. We like to characterize their gases. So we have here Mars and Venus, where we can see the CO2 atmosphere that both of those planets have. But we're really looking for the signature of gases in the atmosphere that look like they could be produced by biological activity, which for the case of the Earth is ozone. So we certainly want to do that. If something like the Terrestrial Planet Finder can't be done in the very near term because of reasons of cost, there are some interesting, simpler approaches that are being suggested. Here is a paper that was published a couple of years ago in Nature for an occulter that could actually be placed externally to a telescope. And if one put one of these petal-shaped occulters in a 20 to 30 meter occulter in front of the James Webb Space Telescope, one could actually, and one moved 7 parsecs from our solar system, one would actually be able to image Earth and Mars. So these are the kinds of things that could be done within about a decade, even with a somewhat constrained budget. Okay, I want to move on to Earth exploration, and one of the things that I have been a very, very strong proponent for is a renewed commitment to observation of the Earth. I think it is essential that we take up and rejuvenate Earth monitoring, and John Holdren gave some examples about the gaps that are there, and it is very pleasing to see that the administration is taking this very seriously. I'm going to give you just one example of the kind of monitoring that would be very useful to do, and believe me, there's quite a bit more than this. This is an image of the Antarctic continent, and we really need to make very quantitative measurements with small error bars about how ice sheet volume is changing and about how ice sheets are flowing. So here are some measurements of estimations of ice sheet flow. We don't have these going on a regular basis. We have conflicting estimates of what ice sheet volumes are. There are some ideas of missions that could go in and measure this very precisely. This is the Destiny mission, which is an L-band interferometric radar system, which could go in and measure that. And we want to know the flow properties. We want to know the amount of water within the ice sheets. We want to know about the lakes that are forming beneath the ice sheets, which we're making attempts to estimate, but it's done basically by field work, because this lowers the viscosity at the base of the ice sheet, and it accelerates slip, reduces friction and accelerates slip and accelerates flow of the ice sheets into the oceans. And it appears that the ice sheets are decreasing in magnitude faster than the models predict, and this is a part of it, and it is something that we need to understand. So this is a plot of, this is an orbital radar measurement of ice cap layering. It's about 700 or so kilometers across, and this is actually a figure that I showed in a talk last week out in Chicago, and it's actually the planet Mars. It's not the Earth, okay? And I had somebody raise their hand at the end of the talk and say, could you please convince NASA to fly one of these around the Earth so that we could get the same kind of measurements for the Earth that we have now for Mars. And we have, in fact, also measured from a satellite snow accumulation over the seasons on Mars before we have done that for the Earth. So there's a variety of things that we've been able to do for the planets that we haven't been able to do for Earth. So when we talk about challenges and opportunities, one of the things that we can think about, we've taken quite a number of observations of Mars over the past decade and a half or so. In some ways, doing Mars is easier than Earth. In some ways, doing it is harder. It's farther away from the sun. It's harder to get to. There's a lower solar flux, so it makes it more challenging to power instruments. So you need lower power instruments. You have more issues with data rate. You have higher surface gravity on the Earth than you do on Mars. Earth has an atmosphere which is problematic in terms of how low an orbiting spacecraft can orbit, because drag decreases the size of the orbit. Earth has a surface ocean which causes complications. Mars has no surface ocean, although it has appears to have a frozen underground sea. On Earth, we have the advantage of a GPS constellation, which is essential in helping us with positioning, and we don't have the advantage of that on Earth. But here, I think, is what I think is the biggest advantage of working on Mars up into the Earth. On Earth, there's national security concerns with some of the observations that you take, and there's politics about making some measurements that would be controversial or not favorable for business interests, and those problems don't occur for Mars. I do both Earth research and planetary research, and it is so much easier to make the case to send an instrument to another planet than it is on Earth, and something is fundamentally wrong about that. And so I really am very hopeful that in the new presidential administration that we're going to set that right. Finally, I want to talk about the challenge of finding life beyond Earth. And I said seek life beyond Earth, not necessarily find it, because we don't actually know that it's there, but whether it is or not is very fascinating. And let me just give you a few examples of fantastic places to look. So first of all, the planet Titan, which is being magnificently revealed by the Cassini spacecraft, which is in its extended mission. Titan is the only other planetary body in the solar system that has a nitrogen atmosphere like the Earth. The radar observations of Cassini have shown the presence of liquid methane lakes at high latitudes on that planetary body. It would be a fascinating place to land on the surface and look for evidence of carbon-based life forms in the outer solar system. Europa, we now have very good evidence from magnetic induction measurements that have been taken by the Galileo spacecraft that there is a subsurface ocean around Europa. This is an area of Europa called commemorate chaos. The big question is how deep is this ocean beneath the surface, and is this ocean accessible? So this is an area that appears pretty frozen, and actually as an analogy, this is a Landsat image, I believe, of an area off the Wilkins ice sheet in Antarctica, which has very many morphological similarities to this area on Europa. And this area here has occurred where the ice has slid off the Antarctic continent, and then ice blocks have tilted over. And so these different colors that you see here correspond to the presence of salts, which indicates that the water below had contact with the surface. We don't know how long ago it is, but certainly looking for thin areas on the ice. And this is a very non-readable chart, but estimates range from hundreds of meters in some places to many tens of kilometers. And it would be extremely challenging to get to, but very much worth it. And then finally, the last area that I'll talk about is looking for life in the subsurface of Mars. So this is what I'll call the frozen subsurface sea on Mars. And this, what you see right here, this is a map of not water. It is a map of neutron flux. And where you see blue means that there is a lack of neutrons being emitted from the surface. Neutrons get emitted due to the imposition of cosmic rays onto the surface, and water moderates neutrons and it picks them up and makes heavy water. So when you see a lack of neutrons, it's a good bet that there's water beneath the surface. And this is the instrumentation here, which is on the Mars Odyssey spacecraft, which is currently operating, indicates that in some places there is more than 70% by volume water ice in the top meter of the surface. We don't know exactly how deep this goes, but as you go deeper on Mars, Mars is a very fractured surface because it has been impacted. There is the thought that the crust is very fractured, which makes it a fantastic reservoir. So if Mars had a surface water, ocean or lakes, that there could be water that was on the surface that is deep in the crust, and if it has the porosity and permeability similar to the moon that we measured during Apollo, it's easy to fit an ocean beneath the surface. But the best place to look for life, I would argue, is where it's warm and where it's still warm. And so the idea is to go to Mars and drill. And this is where you could really use humans. So this is a place where humans would contribute very, very significantly in a way that a robot would have a difficult time doing. And so I'll just close by saying, the things that I've talked about range from very, very doable, almost routine from a spaceflight basis, to being what I'll call flagship class, to perhaps a submarine on Europa, and that's pretty long range and very difficult to do. But the question of could we send people to Mars, and could this be done in the next 40 years? Whenever I design a space flight mission, I sit down and I try to sketch out how many miracles do I need. And if it's more than 2, I work on something else for a while, okay? And because there's only so many things that you can solve and get your experiment into space. So we're going to have a new crew vehicle. We need a heavy lift launch vehicle. We need a surface module. We need a whole class of new spacesuits that allow astronauts sufficient mobility that they don't get weighed down and tired. Mars has a higher G than the moon, and it's very rocky in many places, so we need to think about the physiology there, and some of this work is actually going on at MIT and making good progress in this area, and we need transportation. So there's a lot more than 2 miracles technologically that are in this slide. But let me just close here by saying what a wonderful thing that it would be. I believe these technological problems could be solved because smart people want to work on them. And I'm just going to close here with the hopeful thought. This is a picture of Earth taken from the surface of Mars, from the Mars Exploration Rover landing sites. And imagine the idea that maybe one of the students who are sitting in the auditorium today could see this site for themselves within the next several decades. Thank you very much.
So thank you, Maria, for that tour de force. Since we're talking about the future of space exploration, we're going to use a technology of the present rather than the past and take questions that are texted to my phone. The text number will now appear. So all of you who know how to do this, go ahead and ask questions, and the rest of you should learn. I see the first text question has come in. It says, Professor Zuber, if you were hypothetically to advise a member of the Augustine Committee on the priorities of humans and robotics working together within the Earth, Moon, Mars system, how would you rank those priorities?
Within the
Earth, Moon, Mars system.
Okay, so...
And the rest of you can start texting, because that was mine.
Okay, all right, great. Okay, so actually, one of the things that I think would be fascinating is I think it's important that humans have access to low Earth orbit, because once you're in low Earth orbit, you're out of the gravitational well, and then you can do anything you want, basically. But I would like to see humans get out of low Earth orbit, and even in the Earth, Moon, L1, L2 system, I think is a good place to be, and I think it's worth giving some thought. I was very inspired thinking about the thought of seeing the earliest universe when I was doing some reading in preparation for this talk, and there's been some thoughts about deployable mirrors and inflatable mirrors. And people are thinking about these, aerospace companies are thinking about these, university researchers, and I think that humans could be quite enabling in these things. We had humans fix Hubble, and fortunately they were able to do that. There were thoughts about actually repairing Hubble robotically, and I remember during the Aldridge Commission seeing a fantastic video about how a robot would do it, and the people trying to push this said it would be cheaper than a shuttle flight, and there was no way that that could happen. But I think in the Earth, Moon, L1, L2 system, humans in space could be deploying new kinds of mirrors that would have vast observing power.
How about a human Phobos mission? Would it be worth sending humans to rendezvous with Phobos and bring back samples?
The Phobos, the moon Phobos.
Yeah.
It certainly could be done, and it's certainly feasible. Would I recommend doing that over something else? What I would do is, being a practical person, I would look at the technological feasibility of doing that versus something else, and I would, I'm all for doing what you can do, rather than something that's more difficult to do.
How do you think a layperson can best support the space program? I have about 20 now, by the way. I'm going to take two or three more.
How a layperson can best support the space program? Vote, okay? And you've all done that, or most of you people have, because we had a great outcome in the election. I think people just by their appreciation of what's gone on, their participation in the blogs, their support of education, all of that really contributes to the space program.
What do you think about ice at the south pole of the moon?
What do I think about ice at the south pole of the moon?
Are we going to find it when we smash into it?
Well, I'm sending an experiment to look for it next week, so
we got that one taken care of pretty fast.
But I'll talk about it. So there's hydrogen at the south pole of the moon, okay? But what doesn't get a lot of airplay is that there's hydrogen in areas of the moon that see sunlight every month, okay? And so to me, the big question is this hydrogen ice, or is it implanted solar wind nuclei? And the fact that you see hydrogen in areas that are not shaded most of the time suggests to me that solar wind is at least a part of it. So, and I tend to take things conservatively, but I also believe in actually collecting data.
Last question. Why do we keep focusing on Mars? Why don't we spend more time on Venus?
Well, Venus is a great, so there has been a remarkable Mars program for about the last decade and a half, and I feel very gifted and honored to have been a part of that. There was a remarkable mission to Venus in the early 90s, the Magellan mission that mapped the surface. I believe in the budget rollout that Mars is not going to be its own program anymore. At least there's discussion out of it, and Mars is going to be considered in the context with the rest of the solar system. So that may address that question that the person has. But what I will say is that before Venus had its greenhouse, if it had the right cloud cover and before it lost its water, it actually, models indicate that for a period of time, it actually could have been quite clement. So if we're looking for a planet where there was past life, there's a small chance we've been looking in the wrong place.
Thank you very much. Can you take that? By the way, that produced about 16 questions. 16 questions or comments, including "I like your tie." So I'll invite the panel now to come up here, and as they do, I'll give you law number 2 of my 3 laws of spaceflight. No one is likely to make money in space, as opposed to launching into space. No one is likely to make money in space moving atoms, only moving bits and photons. If you notice that virtually everything Maria talked about, it was images, it was measurements. This is in the information sphere. And the question is, will anybody ever make money in space by doing something with stuff, with real molecules? So for example, here's the question I posed to the students in the space system design class. If you were to fly to the surface of the moon and find sitting there something that you put into your spacecraft and brought it back to the Earth, what would you have to be able to sell it for at $1 per pound or dollars per kilogram in order to make money as a business proposition? And what would that substance be? Okay, you can think about that. Now I'll introduce our panel. Let's see. From this side is James Garvin, who is the NASA chief scientist. Chris Scalise was not able to be with us today at the last minute. There's a flight readiness review, right?
Absolutely.
So Chris is doing the job of an acting NASA administrator being at the Cape, and we wish that process well. James Garvin is the NASA chief scientist, works on strategic issues at NASA, particularly in helping formulate the vision for space exploration. He worked on the first orbiter-based use of a shuttle laser altimeter around the Earth, and he is, in fact, leading the studies of future missions to Venus. Richard Garriott is a computer game developer and entrepreneur. He's the son of Owen Garriott, who was a Skylab astronaut, which makes him the first second-generation astronaut when he flew as the 6th private citizen to go to the International Space Station recently. And he's an investor in the space business. We'll have to ask him about that. Erika Wagner is the science director of the MIT Mars Gravity Biosat. She's an alumna of the International Space University and is the executive director of the X Prize Lab at MIT, studying how to incentivize the exploration of space with the use of prizes. Dave Thompson is the chairman and CEO of Orbital Sciences Corporation, is a successful, I would say, space entrepreneur, having founded the company in 1982 based on a business plan idea that he wrote while he was finishing his degree at the Harvard Business School. Orbital has launched over 700 rocket satellites and other types of vehicles, and Dave, for his work in the Pegasus program, was awarded the National Medal of Technology by President Bush 41. Jim Crocker is the Vice President and General Manager of Sensing and Exploration Systems for Lockheed Martin Space. He's responsible for a wide range of business lines associated with space missions and spacecraft. And among the things he's worked on were the corrective optics for the repair of the camera in the Hubble Space Telescope. And his team, which, by the way, Jeff Hoffman, the moderator in the morning, was the one who installed. And his team successfully prepared the Phoenix lander, successfully prepared and landed the Phoenix lander on the North Pole of Mars. And then there's Maria at the end. So, welcome. So we're going to follow the same format that Ian did and just ask the appropriate leading questions down, and we'll give everyone about 5 minutes to respond. And I'll take some more questions at the end, including some of the ones that were texted in, which are really more appropriate for other panel members. So, James, what's NASA going to do in the future of space exploration to help?
Well, thanks, Ed. Could I have the clicker, since I thought images are sometimes better? Well, NASA's programs, of course, are guided by many of you. In fact, I thought before I answer, I would ask all the people in the room that worked on Apollo or the Space Shuttle or the International Space Station to stand up. Because those of you that did that have given us the legacy, the shoulders of thinking beyond. And let's have a little hand for these colleagues. They've done it. Thank you all. Buzz. Thank you. So in crafting an answer then, if I may have the first slide, thanks. I think we have to look beyond Apollo and remember that what Apollo was pretty much all of NASA at the time that it went forward. And in fact, it was both catalytic and it gave us the confidence to do the next great thing. And so what did NASA do next? It diversified. And this is part of our, if you will, our legacy from Apollo. We diversified from being on the moon and doing the great science that Maria talked about to great advances in propulsion and aerothermal engineering, some I know happened here at MIT. And the shuttle gave us, maybe to many people, a mixed blessing. It extended human spaceflight to low Earth orbit, and it seems to some that we've been grounded there or flying there forever. However, that's not really the case. It's important to look at the record. What did shuttle do? Well, it's constructing International Space Station, our next great national laboratory in space. It also flew missions of discovery. The first ever global map of most of the Earth's topography was made from the shuttle in a way that only the shuttle could enable. 5 servicing missions to Hubble, extending its life initially by Jeff and others after it was broken. This legacy was a combination of human spaceflight and robotic spaceflight that is really the hallmark of the NASA that we're now proceeding with. In addition, I think we need to remember that one of the things NASA does best is to build capability. The science is done in the universities and the national laboratories. The capabilities that are now on the table to be developed for the extension of human presence in space are all about those miracles that Maria was talking about. What do we need to do that? Well, we need access to space. You can't do things in space if you're not in space. I think my second grader gets that even. So given that, access to space needs to be assured. One of the big hallmarks of the last 10 years was the recognition that separating crew from cargo is important, and hence a fleet of Ares launch vehicles to carry both the crew in an Orion capsule system borrowed from the great legacy of Apollo, but also to a heavy lift launch vehicle, the Ares 5, to carry the consumables, the big stuff. And in doing so, also enabling things that we could do robotically that we can't do today with our current fleet. The other thing that's very important to recognize in this picture is the Earth departure stage. The propulsion system that carries people from beyond the gravity well to where we're going is vital. It worked beautifully on Apollo. Buzz is sitting here, absolutely got him home as testament to that. We haven't been back to that kind of technology since those days. We don't have human-rated in-space propulsion systems. So this capability space I'm showing here is the plan for NASA, with the public support of this administration, to go forward. And it will leave the gaps that John and others talked about earlier. In addition, we have ideas beyond that really focus on looking at the Earth as a system beyond where we are today. And Maria touched on this. We are in a revolution of understanding the last 30 or 40 years of the Earth science record. The National Academy Decadal Survey for Earth Science recommended 15 new missions, several with revolutionary technologies. I like to show this picture because it looks weird, but it's an image of this mission called Destiny, whose primary job, other than looking at the ice, is to measure basically the sources and sinks of carbon. And as we go to a carbon offset economy and look at cap and trades, how much carbon are we sequestering? How much is there? What is the record of that carbon? Is it locked up in the boreal masses, or is it in the ground? How is it in the oceans? We don't know. We have a missing carbon problem on Earth, and it's not just the hydrocarbons we burn. Missions like this and others, recommended by the Decadal Survey, are in our future. And this is an artist concept of the 2015 Destiny mission. So looking at the Earth is very important. Finally, my last comments, I'd like to really talk about what's happened in the last 40 years and look beyond. So it was to have been a space age. We went to the moon, we did all the great things, not because they're easy, but because they're hard, as President Kennedy said. I can't help but saying that, it sounds good here in Boston. But anyway, what actually happened was human spaceflight focused on aerothermal engineering, shuttles, and space stations. And robotic spaceflight took over. And I like to show this picture of the Mini Cooper-sized, no offense to other auto manufacturers in the room, the Mini Cooper-sized Mars Science Lab, now named Curiosity, by a young girl. What's important about this picture is, in 1972, many, not here, but in other places, would not have believed this is possible. A 950-kilogram autonomous mobile analytical laboratory carrying gear as sensitive as any in the United States on the ground when the Apollo samples came back in '69. That's in that now. And the price of this vehicle is 1/6 the price of the Viking mission we flew to Mars in 1976 in our first foray to look for life beyond. We have gotten better. And this is evidence of what has been a robotic information age as we've learned in human spaceflight to now dream the bigger dreams. So let me conclude with a couple final thoughts that echo Maria's comments about science. I think this picture says it all. Somewhere there is a sweet spot, and it's a realistic sweet spot between the robotic spaceflight that does the grand science, the grand challenges, and the human spaceflight that enables those. And whether it's drilling on Mars, or erecting gigantic inflatable telescopes, or erecting giant apertures to look back at Earth to measure the radiative balance and other drivers of our climate, or looking at the sun, you can all imagine them better than I. That's a hallmark of our next 40, I think. And here's John Grunsfeld, an MIT grad, go John, doing what was not imaginable by the robotic servicing plans that Maria talked about after the Columbia disaster. And this all happened just 2 weeks ago. So this is our future, and how to extend this to the surface of the moon, or to a NEO, or to Mars, is really the ultimate question. So I'd like to finish with one final thought, which is, it's appropriate here in Boston, you see the bridge, that ultimately the question comes down to the capability to get there. And Earth to orbit and orbit to space is what we're all about. In the next 40, I think we'll see that revolution coming from NASA.
Thank you. Richard, I actually have a question for you to lead in. This is symptomatic of the future generation. Are you ready for this? Why does Richard still have a Padawan-style haircut? He's been in space now. He must be a Jedi Knight.
I think that question must be referring to these, my rat tails here, which I have to tell you I've had since before it was cool, before Star Wars, through the period of time that it was cool, during Star Wars, and now long after, so for better or worse. But also earlier you had asked me to talk about the role of the real question, yes, the real role, which is what are the potential roles of this fledgling new entrepreneurial private space industry that is that I've had a chance to play a part in. What's its role as this new era is upon us? And I first have to start out by just saying that I grew up in a neighborhood believing that every one of us was going to go to space. I mean, my father was an astronaut. Both my right and left-hand next-door neighbors were astronauts. My back fence was an astronaut. Buzz and Neil were nearby in the neighborhood. Everyone was either an astronaut or an engineer or scientist involved in putting people into space. So I grew up, I think lots of kids grow up believing that they want to grow up to be an astronaut. I just assumed everybody went because everybody I knew did go. And it was a real shock for me when I was a young teenager and a NASA flight medicine, a NASA doctor actually told me that my poor eyesight meant that I was not eligible to be selected as a NASA astronaut. And so at first it was crushing because it was like being told you are no longer eligible to be a member of the club that your father and all of his friends are members of. After getting over that shock, I then decided, well, look, who are you, one source NASA, to tell me that I have no ability to go to space. So I said, if I'm going to go, it means I have to go privately. And if I'm going to go privately, it means a private space industry has to come into existence. And being young enough not to realize how incredibly difficult a problem that was, I set off as an investor to bring into existence private spaceflight. And I was very fortunate that at a young age, I also discovered computers and had a very successful career in the computer game industry that Ed mentioned. But with pretty much every dollar that I invested personally, I invested in the privatization of space. I invested first in organizations like SpaceHab, which part of their original business plan was to put people in basically a double-decker bus in the back of the shuttle payload bay before I realized that the politics of that made it effectively impossible. I invested in a number of the fledgling suborbital spaceplane companies even before we started something called the X Prize. I was one of the founding board members of the X Prize, founding supporters of the X Prize, Zero G Corp, and ultimately Space Adventures, which is how I finally arranged my flight into space. And not only was, that took about 30 years to pull off getting myself into space. However, I think that's pretty good. I mean, considering that I'm still, I'm under the number 500 for number of people who have been into space. So I think the probability of pulling it off at all was pretty daunting. So I still feel pretty darn good about 30 years being all that was required to get there. And of course, when I went, I didn't know that the private space industry could pull it off at all, or that frankly it could continue, or what role it would play in the future as it's now playing out. What I'm actually very excited about is that not only has this journey allowed me to go, but I'm actually extremely bullish on not only the role that they are playing now. For example, with the X Prize, we've scaled composite Spaceship One is now hanging in the Smithsonian. Virgin's now buying Spaceship Twos. Elon Musk with SpaceX is already flying to orbit and will be taking cargo back and forth the ISS for NASA under the, I think, brilliantly conceived COTS program, which is something I'm a big fan of. But also a lot of the other suborbital makers, whether it's Blue Origin, X-Core, or one of my favorites, Armadillo out of Dallas, Armadillo Aerospace. Those guys are all now going to be making journeys back and forth to space. And not just suborbitally, but most all of them have plans to continue on to orbit. And as you might imagine, my life since my flight has been often to come to places and times like this to speak about the evolving business of space, or to brainstorm about possible ways to monetize space when you get there. And people even today have challenged the students here at MIT to come up with ideas for how to capitalize on access to space. And I have to say that I actually think that people are challenging students often with the wrong question. Because I think that the probability of students being able to justify tens of millions of dollars per person to orbit is actually unlikely. I think that especially as a private enterprise investor, that's a very difficult nut to crack. I instead would rephrase the question, which is, I myself on my own flight did work that paid millions of dollars, not tens of millions, but at least a significant percentage of my flight cost. And so if we can get flight costs down to a mere millions of dollars per person, then an interesting event will occur, which is the changing of positions of the cost of access and the value you can return with. And I believe that will happen within the next 5 to 10 years. And I believe that this fledgling private industry that I'm a part of is already on the journey to making that happen. And so my challenge to the industry and to students is to help that journey along, to help bring into being something that in my mind is inevitable. And so the question is not whether it will come, but when it will come and who will be a part of it. So my challenge again to MIT students specifically is to become part of that journey. And my challenge to government space programs and private, what I call traditional aerospace, is to find a way to partner with and capitalize and take advantage of the technologies that this fledgling industry is bringing to bear versus resist it or ignore it. So thank you.
Great. Richard, since you've recently been up and down, and that's not a golf shot, by the way, there are a couple of questions that came in about safety and the importance of safety in the human program. You rode up and down on an extraordinarily reliable vehicle. It doesn't happen to be the one we operate. You want to comment about sort of what you think are the risks and rewards and the safety considerations for a second?
Yeah, well, like you mentioned, I was lucky enough to travel on a Soyuz, which is actually a phenomenally reliable and safe vehicle. I think the Russians have a vastly underrated, by what I'll call the general American public, space launch system. Even I thought of the Soyuz as an old system until you get there and start training on it. You realize it's actually been updated constantly through its evolution, and even though its physical profile is similar, they've continued to improve the quality and safety of that machine, quite a bit. But when you talk about safety in the general purpose, there's no question that if you're going to travel into space, you need to do it cost effectively, you need to do it safely, and you need to have a real good purpose to be there. And I think that's something that at least the American public can't see very well yet. And I think we've not done a great job as an industry to either prove the case for it or at the very least communicate that to the general public. But as we build new space vehicles, whether they're the manned systems NASA is going to build or some of these more barnstorming-oriented capabilities that this new space industry is going to build, there's no question that there will be a new phase of risk. At least for the first dozen or two flights of any of these vehicles, the precise math of the risk is going to be unknown. And so therefore, I think there's a reasonable probability that we'll have fatalities, for example. But I think there's no question that that is worthwhile. And I personally would take those risks myself on some of these new fledgling technologies that come into existence. And I think that ultimately only by what I will call democratizing access to space, by having multiple vendors competing to keep the price down, competing to keep safety up, will we ultimately find the best access to space.
Thank you. Erika, you're the token young person on the panel here. So I asked you to think about how we can engage the youth of America in thinking about the future. There are endless, and in fact, in President Obama's presentation at the National Academy, numerous citations to the degree to which Apollo excited the youth of America, inspired us to study what's now called STEM, science, technology, engineering, mathematics. And yet, I find in dealing with our students here, they're not really very excited by the current plan. They sort of think it looks like something their grandfather did, or maybe their father did. What do you think, Erika?
Well, first of all, let me just say it's an absolute honor to be up here. I've been sitting down for last night and this morning, watching as one after another of my heroes came up on stage and sat in these seats, and I was thinking to myself, oh my, this is going to be an incredible place to be. So we've already asked those who have helped create the history of space to stand up, but could everyone who was born after Apollo 11 launched please stand? For those of us that were born after Apollo started, this is a given. We've been to the moon. We're going to go back to the moon. This is a part of our generation's heritage. So I welcome all of you who are standing to join me, because this is our future to create. And we have some really big shoes to fill and some really incredible opportunities. So I was asked to think about how we recreate the spirit of Apollo, and I think it fundamentally takes three things. We need to amaze people again, we need to engage people again, and we need to connect with the next generation. If we look at Gallup polls over the last 20 years, the American public is actually fairly strongly in support of NASA and in support of space exploration. The latest polls for the Vision for Space Exploration show 67, 70, 65, large overwhelming majorities of the public support what NASA does. But there was a recent study of 18 to 24-year-olds, and it asked them what they supported. And when you look at it, only 1/3 actually supported returning to the moon. 27% of the 18 to 24-year-olds that were surveyed had doubts about the fact that we had ever been to the moon. That's over a quarter of the young people in this country that were surveyed have doubts that we ever went. And it made me stop and think, why, for me, this is an absolute given. But for a generation that grew up with Challenger, with Columbia, with a space station that's been hamstrung by budget and schedule overruns, it's no wonder that they doubt that we're capable of doing incredible things. I think if we want to get the next generation engaged, we have to do amazing things again, and we have to take back the storyline and talk about what's hard. And I think that Kennedy had it right. We were going to go into space because it was the difficult thing to do, and that was how we inspired the next generation, and that challenges are good. When President Bush stood up to announce the vision for space exploration, let me just quote from him. He said, "We will begin the effort quickly using existing programs and personnel, and we will make steady progress." That's not really, we're going to go to the moon in the next decade. It's not inspiring, it's not challenging. It is challenging to do, but what we need to do is we need to take back that storyline and start to talk about the challenging things, because if we can amaze the youth, then they will do incredible things. We also have to engage the youth. As we've heard a couple of times, the average age in mission control during the Apollo 11 mission was somewhere between 26 and 28. Right now, if you look around NASA, there's less than 20% of NASA is under the age of 40. If we want to be inspiring the next generation, we have to be engaging them. They have to believe that they can go and do these things, that they can be a part of this new vision. So we have to do amazing things. We need to engage the next generation in doing them. And we need to reconnect with the American public. How many of you remember reading Life magazine during the Apollo era? Or watching launches on the evening news? Well, Life magazine, not so much anymore. The average age in recent surveys of people who watch the evening news is over the age of 60. We need to find new ways of communicating the incredible things that we're doing with the generation of tomorrow. We need to use Flickr and YouTube and iPhone apps and texting questions to our moderator and tweeting. Anyone who happens to be on Twitter today, we're at #Giant Leaps. In that vein, I think it's time for space exploration to become interactive again. And what Richard was talking about, the emergence of the commercial spaceflight industry, is really an incredible thing. In September of 2004, I had the great chance to go out to the Mojave Desert for the launch of Spaceship One. And I stood there, and I was stoked. I was really excited to be there. But I was also watching the people around me, and we saw Scott Crossfield, who flew the X-15, and the NASA administrator, Sean O'Keefe, and half a dozen astronauts. And I tell you, they were kids in a candy store. And these were people who had seen hundreds of launches, satellites and shuttles and Mercury and Apollo. And this is something new. This was changing the whole game. And I think that the promise of being able to open up space to the public is something that's really, really interesting and important. In 2007, the X Prize Foundation announced its next space challenge, along with Google, $30 million in prizes for the private explorers to return to the moon, to rove around the lunar surface, and to broadcast back HD video. And we've seen 18 different teams from around the world that are coming out to compete in that. And I'll go ahead and shout out to the folks that are working on the next Giant Leap team here in Boston. Students and faculty at MIT, at Draper Lab, at Aurora Flight Sciences, with the Sierra Nevada Corporation. You may have seen some of their prototype hardware hopping around over at lunch. And this is the real deal. This is how you invest in the next generation. You challenge them to do something amazing. You engage them from the day one all the way through operating the hardware. And you share their stories, and you let them share their stories in ways that resonate through blogs and tweets and YouTube videos. So I'll just close with a quick personal story. This January, I had the incredibly humbling experience of being invited to Houston for the first round of interviews in the astronaut selection process. And this was an absolute dream come true. But the best memory for me was we got called at dawn to come to work out with the personal trainers at the astronaut gym. And we walked in, and they sent us off to our locker rooms. And it was like that scene in every sports movie you've ever seen where the rookie walks in and goes, oh my gosh, that's Joe White's locker, and that's Jim Green. But for me, it was Eileen Collins and Janice Voss and Katie Coleman and Sonny Williams. And I'm a space geek through and through. And I know that today I'm preaching to the choir. But we're here today because we believe that amazing things are possible again. And so I think that the challenge is to share what we know to be possible with the rest of the public and to invite the next generation to take the reins and come along for the ride. So thanks.
So what, in addition to twittering and texting, what could we do to sort of reach out and grab this generation? I mean, it's remarkable to me how often and how deeply it is felt inside the Beltway that the primary motivation, the primary national urgency to have a successful human spaceflight program is to inspire the youth. And if we don't have one that inspires the youth, it erodes that enormous base of policy support. Can you think of a few things we might actually do?
Fly students.
There you go.
First and foremost. And I don't care if it's suborbital.
Or fly students' experiments, even.
Fly students' experiments, but fly students. I mean, we're coming to the age where we can do that. And I think the advent of suborbital flight, we should be flying students.
Even that Padawan next to you got to fly.
Indeed, indeed. And I think that when we do incredible things again, the students will be excited again. And we have to learn how to tell those stories.
Do incredible things and fly them. Yeah. That's your advice.
Simple.
Good formula. David, you've built up a successful commercial enterprise doing business in space from a garage-based operation 20 years ago, 25 or 7 years ago. How are companies in your category going to contribute to this great endeavor?
Ed, it's 27 years, 2 months, 9 days, and 4 hours and 20 minutes, but who's counting? Good afternoon, everybody. The tagline on the program for today, perspective is everything, I think is important. And perhaps to add a little bit of perspective from the standpoint of several other sectors of planet Earth's space enterprise, I would begin by talking a little bit about the current state of affairs in the commercial space sector. Commercial space today revolves almost exclusively around satellites that provide communications, navigation, and imagery services to consumers on Earth. And over the 40 years or so since they began in the late 60s, they have grown to represent the largest and the fastest growing sector of the space market today. Based on the numbers that we compile, which are a bit more conservative than some that have been published, last year individuals, companies, and government agencies spent about $185 billion on space-related activities around the world. And these categories of communications, navigation, and imagery generated about $110 billion of that total, so roughly 60%, which makes everyday uses of space for these kind of applications a little over 3.6 times as big today as all scientific and human spaceflight combined, and even 2.25 times larger than the amount of money we spend on important military and intelligence space activities. In addition, over the last 15 years, these commercial applications have grown at about twice the rate of government applications. Last year, they expanded about 9% compared to the prior year, compared to 4 or 5% growth across all the various governmental space activities. Now, you may wonder, how could this be possible? Well, Ed's example earlier of a New England boy, professor now at MIT, commuting all of 3 or 4 miles back and forth in Cambridge, listening to satellite radio, is really the answer to that. There are some 350 million people on Earth today that every day receive information in one type or another directly from satellites. And that doesn't count several billion people that receive it indirectly when we watch the Weather Channel or we turn on our TV sets when we're subscribers to terrestrial cable systems. Commercial space systems have achieved these impressive economic results because of a steady pace of advances in technology that have been applied primarily to reducing cost. Over the last 30 years, the capital cost per transponder year of satellite communications capacity has fallen by a factor of 25. So if you do the math, that says year in and year out, some years have been better than others, the commercial satellite communication industry has improved its primary economic figure of merit by 10 or 11% per year. When you do that for 3 decades, you produce 25-fold improvements in what matters to customers. Now, this has not been the result of any single breakthrough in technology. It's been a series of sometimes large, sometimes relatively incremental improvements in a variety of both space segment technologies as well as the ground equipment that many of us use to receive this information from satellites. In addition to the contributions of well-established companies that grew up during World War II, the Cold War, or the Apollo program during the 1960s, many of these advances have also been propelled by a great deal of entrepreneurial activity. In the last 40 years, by my count, there have been almost 350 new companies started, and we've seen about 75 of those companies succeed to the point of actually being able to build, launch, or operate at least one privately owned satellite. The largest of those today is an American company that broadcasts hundreds of channels of entertainment television to half-meter diameter dishes throughout the U.S. and other locations in North America. One of the other large ones, generating something like $3.5 billion a year, sells GPS-enabled smartphones and other consumer products that use the Air Force's global positioning system in ways that were never imagined when that system was conceived back in the late 1960s and 1970s. In economic terms, then, the commercial space sector today generates by far the highest value space benefits based on the way markets assess these benefits. While most of us here would probably ascribe a much higher value, and we'd be willing to pay a much greater expense for our terrific space and earth science programs that are carried out robotically, the fact of the matter is we have a democracy, and in the political give and take of our democracy, we have assigned a value to that in the United States of about $1.50 per month per citizen. If we throw in the weather satellites, we'll pick that up to about $1.75 per month per citizen. All of us would agree that's got to be the best bargain we've ever seen, but our democracy assigns that value in its allocation of resources to the robotic space program. The human space program does a little better, but not a lot. For at least most of the last 30 years, NASA has, in many cases, been right on the ragged edge of doing what can be done with the resources allotted to it. In today's dollars, the democratic process that we follow in our country assigns a value of about $3 per month per citizen to our human spaceflight programs. The defense and intelligence programs in space, which have played a role that is not widely recognized throughout our country in allowing the Cold War to come to a peaceful conclusion and to do many other things in more modern times to protect our country's security and that of those young men and women that we send overseas to be on the front lines, generates a little higher perceived value. As a country, we spend about $10 a month per citizen on all of our space, defense, and intelligence programs. Well, of course, if you multiply any of these numbers by 300 million people, you get sizable sums. What is significant, though, to me is that in a somewhat quiet way over the last 40 years, commercial space ventures through the development of direct broadcast television, handheld satellite navigators, satellite radio, satellite imaging, have found markets where customers voluntarily spend between $15 and $25 per month per subscriber for space-delivered commercial services. These areas, I think, provide a very strong foundation for growth across all sectors of the space enterprise in the years ahead. Now, there's not a particularly easy fit between the pressures and the demands of many government space projects with those that are carried out entirely by the private sector. For instance, the private sector typically takes its technology advances in small increments. The government, often because we only get the chance in the public sector to develop one or maybe two new space systems in a generation, has to take a little more risk sometimes as we introduce new technology. Commercial satellite systems have very well-defined objectives. They're implemented over a 2-year period, and we almost never change direction once we start a project. Of course, as you know, public sector ventures responding to a somewhat more diverse set of constituencies often take a lot longer and do change their objectives over time. There are many other reasons why there's not a particularly natural fit between these sectors, but I am encouraged by progress that's occurred over the last 10 or 15 years where the degree of intersection and overlap between the sectors is increasing. Today, for instance, almost $5 billion will be spent this year by government agencies in the United States, Europe, and elsewhere, buying from commercial providers products and services that those providers also sell to companies and individuals. Probably the best single example of this is in communications, but there are other examples. NASA has a new program underway now for commercial delivery of cargo to the International Space Station that will quickly develop into something like a $500 million a year area of intersection between those segments. And so with these and other examples on the horizon, I'm hopeful that we will see more interaction between the three sectors of the space enterprise that have largely grown apart over the past 40 years. It was notable to me that just a couple of months ago in Washington, I attended the largest commercial satellite conference of the year, which brings in all of the commercial satellite owners from all around the world. Attracted some 9,000 people to this conference the third week of March. 2 weeks later, I attended the largest civil and military space conference held in the United States in Colorado Springs. It attracted about 7,000 people. In these two sets, one numbering about 9,000 people, the other about 7,000 people, I estimated there were about 300 people that attended both conferences. So we have two worlds dealing with many of the same underlying physical principles, engineering practices, and technology base, who more or less don't speak to one another. And I am hopeful that over the next decade, we'll find many more areas where these two worlds can intersect to the benefit of both. Thank you very much.
Dave, you'll be happy to know that due to those inspiring remarks, the stock closed up today. Sort of sounds like a CEO, doesn't it? Our final speaker is Jim Crocker. How can what we'll call big aerospace respond to the needs of the future of the program?
Well, thank you, Ed, for giving me 5 minutes to answer the question of how we can reduce cost and cycle time in the aerospace industry.
There's another question that if you
Okay.
finish early.
Well, I actually was going to tell you, I think I can do it, but it'll take 6 minutes, not 5. As a matter of fact, unbeknownst to Ed, I've actually spent the last over 30 years of my career actually thinking about this problem and actually trying to do something about it, not at large aerospace companies per se, but large aerospace, medium aerospace, government, in academia, and in 2 startups. So while in 5 or 6 minutes I can only give you a caricature of the question, I think before I give you the answer, I have to tell you what I think the problem is. Well, to begin with, it's not how we build satellites. It's, first of all, how we procure them, because we buy them one at a time. I mean, everybody here at MIT knows the story of why pencils and toothpicks and airliners cost so little today, and it's because fundamentally Ford, while watching the Armour pig plant disassemble pigs, had the idea for how to assemble cars. And most of our prosperity today comes about because of the assembly line and all of the associated improvements that we've made over the decades to do that, from pencils to pigs to aerospace. But with satellites and with launch vehicles and with many of the other things, we buy them one at a time. Now, we try to improve that by buying several at a time, but in essence, we still build them one at a time because we build them to replace the one that's going to fail, and then we launch them on a launch vehicle that we build one at a time, and it costs a lot. And the other secret is even when we buy several of them, we don't build the same thing twice. The last time I looked, the Hubble Space Telescope was 2.4 meters in collecting area, and the James Webb is 6.5. That's almost a mass factor 7, almost an order of magnitude bigger, and it's about the same price, but we never build the same thing twice, so we don't get the economies of scale. Now, before you get too depressed about that, I think I can prove to you that economies of scale would go a long way to solve the problem, because Lockheed Martin built the Iridium constellation of satellites, over 90 satellites actually built by the company, launched in multiple launches with clusters of vehicles on each one. And in fact, I've seen the numbers, and they were built for an order of magnitude less and built at fixed price. So there's no magic between big company, small company. There's, in this instance, it was just economies of scale. Now, for those of us who thought that if we built it, they would come, the CubeSaters of today, I think, we had this wonderful production line going. We were building these spacecraft, and we just thought we would just provide everybody with the low-cost spacecraft and low-cost launches that they needed. And lo and behold, nobody showed up. And we had to shut the Iridium line down, which Lockheed thought was a great waste, because we had the volume, but there was no follow-on volume because no one could find the application that, like Iridium, would require a large number of satellites. So it came down to a business model. So in both cases, it's how we buy and what we use them for, and the business model had little to do with the production. The production was driven by how we bought. But Iridium demonstrated, in fact, that you could do something. So we don't have the volume. We don't buy multiple satellites, so what can we do? And in fact, for the last several years, last almost decade at Lockheed Martin, we've been trying a couple of different approaches, which in fact have been working, and it's part of what we're doing for Maria Zuber with the Grail mission, and that is we've been moving the satellites to be very software intensive. Anything that was mechanical or electrical that we could throw off the satellite and replace it by software, that's exactly what we've done. As a matter of fact, it's been extremely successful. I was looking, the Viking lander, just the lander itself, depending on how you do inflation and different numbers, is well over $1 billion. Some people would say 2, certainly north of $1 billion in current year dollars. Just on March 25th, not this previous, but a year ago, which happened to be my daughter's birthday, we landed the Phoenix lander. She thinks we did this for her, on Mars, on the polar region, and that spacecraft was under $100 million for the lander portion. So well over an order of magnitude improvement, and fundamentally it was done by changing electronics and mechanical systems out for software. I had someone run a calculation for me, and I looked at over the last decade alone, a box that is the size of the speaker that you see in front of me, we've been able to reduce by software, and in this case, I'm talking about programmable gate arrays, not just software, to something the size of your fingernail. Now, it's not just the box alone, because the box area that I'm talking about includes the power system and electronics associated with that would have to power that box as well. So you can see an enormous reduction, and that's how we've gotten most recently in the planetary spacecraft the size, weight, volume, and thus cost down. And we're trying to do the same thing with Constellation, with the Orion capsule. It is going to be extremely software intensive. Anything you can do with software, you do with software. Last time I looked, software doesn't weigh anything. You can also reuse it much more inexpensively as the industry, software and computer industry shows. But that's not enough to really continue driving the cost down. The other thing is reusability. And of course, the Orion capsule will be used several times, just changing the heat shield, as will the Ares rocket. Of course, the Ares 1 is very similar to the external SRBs on the shuttle, which parachute in, get refueled, and flown again. But unlike the shuttle, I think what we're doing correctly this time is we're only reusing the expensive parts. The less expensive parts we're throwing away. It's the expensive avionics parts that we're trying to recover, both in Ares as well as in the SRB. Shuttle became so expensive because we tried to make more of it reusable, too many miracles, as Maria would say, to do. And then, so just to sum it up, I'd say software, reusability, new business models, and then lastly, the right mix of humans and robots. It's not humans or robots, it's humans and robots working together, and I think as we've demonstrated on the Hubble servicing mission, some very innovative ways that we can get to a cost that, while it's not going to be as cheap as flying from here to Europe on an airliner, might get us to the point where we can do more with the dollars that the public is willing to spend to allow, quite frankly, all of us to carry them on this journey of exploration and discovery.
Well, let me try and wrap up. There's excitement in space, there's opportunity in space, there's understanding of the universe in space. We should send students into space. I didn't hear anyone violate law number 1. I heard lots of people thinking about how we design our space missions to satisfy the stakeholders, the American public that fund them, and in fact, direct references to considering the investment that we're making on behalf of the nation. I didn't hear anyone violate law number 2, which is that primarily we move bits around in space to gain information and to make money. And of course, we have to build systems that move bits, but the bits are fundamentally what the recurring value is created by. So I'll summarize the afternoon session by giving you my law number 3, which is that all successful human spaceflight endeavors are fundamentally instruments of foreign policy. That Apollo was an instrument of foreign policy, that Shuttle was a vehicle by which many nations launched their first astronaut. In fact, more than 50% of people in the UK, in polls there, believe that the UK launched Mike Foale into space. He's become such a popular figure in the UK, the British astronaut. The International Space Station version 1, created by the Reagan administration, was viewed as the way to collect those battling against the evil empire in a grand alliance to work together in space. The International Space Station version 2, created by the Clinton administration in 1993, was predicated on the fact that the International Space Station was a good way to engage the no longer occupied building the Soviet space vehicles, Russian space engineers into building a joint venture, and therefore keeping them away from building things like intermediate range ballistic missiles for third world nations. And I think the fundamental question, in some senses, that the Augustine Committee has in front of it, or one of the fundamental questions, which was touched on in many of the questions that we didn't have time to get to today, is how will we make this next incarnation of human spaceflight both important to the American people, important to the scientific community, important to the economic community, and fundamentally a successful instrument of foreign policy. So thank you very much for coming today. Thank the panel and the organizers.
You can stay right here.
Well, you're going to sit?
Yeah, you can stay right here.
Okay.
Let me add my thanks to our keynote speaker, Maria. Thank you. To our panelists, thank you all. And to Ed, super job moderating. Very well done. We have had a very busy day. That's not unusual at MIT. But I'm going to make my closing remarks very, very short. This has been an opportunity for us to bring together a couple threads in a new way, and I hope that you've found it engaging and interesting. I've certainly found it very engaging and interesting. It's now time to sort of switch into celebration mode fully. As people are aware, we have a very special show at Symphony Hall tonight. I want to provide just a little bit of direction to you. The most important thing that you can remember from me in my closing remarks is that if you have questions about transportation, go to the registration desk, which is in Johnson, and they will help direct people in appropriate places for buses. There's transport that will go to and from hotels in Symphony Hall. There's transport that will go to and from here. And there are a reception and dinner for everyone over in Johnson. And then there are some people who will go to a department dinner just before the symphony show. And if you are going to the department dinner, the Hunsaker dinner, look for the signs for that or ask some of the people outside who will help. So there's about 4 different vectors of transportation, and the most important thing you can do is follow signs and ask for help. So that's the bit of housekeeping that I wanted to do. As I said, I would keep my closing remarks short, so I will officially close the symposium. I do so with no small amount of personal admiration and inspiration from all of you who contributed to the Apollo program and the space program since that time, as well as today's leaders who shared with us much of their wisdom and thoughts. And the real inspiration for all of us is that group of individuals that Erika had stand up, who were born after the Apollo 11 landing. The real inspiration is that you'll do something great in the next 40 years for us. So with that, I close the symposium, and thank you all.